Welcome once again to my YouTube channel. Today we are taking a topic in physics. Topic: physical quantities and its units. In physics, physical quantity is the bedrock of physics. It's a foundational topic, so you need to pay attention well in order to master it well. Now in physics, physical quantities are properties of an object or system that are measurable. I repeat, physical quantities are properties of an object or system that are measurable. Now, take for example, we have a body, like as I am now. There are physical properties you can observe here. There are a kind of properties of me you can even see. You see my height, though not short, not tall. Now, these my tallness per se can be measured as a length. Now, the length of me can be measured using either meter rule, tape rule, whichever way. Now, as we are measuring these very physical properties, it entails that that very length is measurable. Hence, length is a physical quantity. So there are a lot of quantities that can be measured. You can get the temperature of my system. That's a physical quantities. You can even weigh me. The mass of me can be obtained. Hence, mass is a physical quantities. But there are quantities that are not measurable. For example, as I love you now, there is no instrument that can be used to weigh the love I have over you. Hence, love is a physical quantity but not measurable. My intelligence cannot be measured. Hence, the intelligence is not a physical quantity. So those quantities that are measurable, only you talked about electric current, it can be measured. You talked about pressure of a system, it can be measured. So those quantities that are measurable are termed physical quantities. Now, based on the classification of physical quantities, we are going to do that with respect to two factors. One, we classify physical quantities based on units. Then we classify it also based on direction. Now, classification of physical quantities. So like I said, physical quantities can be classified based on units. Okay? It can also be classified based on direction. Okay, so based on units, we have two types of physical quantities. One, we have fundamental quantities. Then again, we have derived quantities. So these are the aspects of physical quantities based on units. Now, based on direction, we have vector quantity. Then again, we have scalar quantity. So these are the two classifications based on direction. But today we are going to move into units, the classification of physical quantities based on units. Now, coming to units, as we have fundamental quantities and the derived quantities. Now, the fundamental quantities, these are the quantities that are independent of every other quantities. Hence, they are natural quantities. They are not derived. So those quantities that are independent from other quantities are said to be fundamental. They are basic quantities you can think of. In physics, we have only 7 fundamental quantities. Now, these 7 fundamental quantities can be remembered using these very mnemonics I'm going to give to you. The mnemonics, I term it multlet. Multlet. The 7 fundamental quantities, if you know them, every other quantities that are not included in the 7 are said to be derived quantities. Now, the 7 fundamental quantities, like I said, we have what? Multlets. We have multlets. Now, look at we have month, we have let. Now, if you count them, we have 1, 2, 3, 4, 5, 6, 7. They are 7 in number. Now, each of them represents a quantity. Now, coming to M, we have mass. Then A means what? Amount of a substance. Then we have L. It means length. Then T is temperature. The temperature. Then L, we have luminous intensity. The luminous intensity. Then E means electric current. Electric current. Then T means time. Now, each of them has a symbol. The symbol of mass is M. Amount of a substance is small letter n. The length is L. Temperature is theta. Luminous intensity is Lu. Electric current is I. Time is T. Now, all these 7 fundamental quantities has their respective units. When we talk about units, units are standard quantities used for measurement of other quantities. Check, for example, we have length. Length is a fundamental quantity and its unit is meter. So, a meter rule is used to measure length. So, the unit of length is meter, although it has other multiples of units. Multiples and the submultiples. We have kilometer as a multiple of a meter. We have centimeter as a submultiple of meter. But the standard unit there is meter. When I talk about dimension, dimension of a physical quantity is the power of which the fundamental quantities are raised to represent the quantity. Now, let's see them here. We have fundamental quantities. Number 1, we have mass with a symbol M. Then 2, we have amount of a substance with the symbol N. Then number 3, we have length. The symbol of it is L. So number 4, we have time, which is T. Then number 5, we have luminous intensity. The symbol is Lu. Then number 6, we have electric current. Symbol is I. Then finally, we have temperature. Then the temperature is represented with theta. Now, each of these has what we term the units. Now, the units of these fundamental quantities, mass, we have it in kilogram. Now, the symbol of kilogram is kg. Amount of a substance, we have it in mole. The symbol of mole is mole. The length is measured in meter. Symbol is M. The time is measured in seconds. We have S. The luminous intensity is measured in candela. We have CD. Electric current is measured in ampere. We have the symbol as A. Temperature is measured in Kelvin. The symbol is K. So we have this as their respective what units. Now, based on their dimension, Each of them has a dimension. So coming to the dimension of mass, the dimension of mass is capital letter M. Amount of a substance, which is measured in mole. Each dimension of amount of a substance is N. Then the length, each dimension is L. Time, the dimension of it is T. Luminous intensity, the dimension is J. Electric current, the dimension is I. Temperature, we have the dimension as theta. Now with this, you've mastered the what? The fundamental quantities, their respective units, and their dimension. I told you that fundamental quantities are independent quantities. They are not obtained from anywhere. Hence, they are natural quantities. Now, coming to derived quantities, the term derived tells you that they are obtained from somewhere. Hence, derived quantities are those quantities which are obtained by combination of two or more fundamental quantities. So when you have two or more quantities which are fundamental, if you combine it to obtain another quantity, such result is said to be derived quantities. Take for example, when you talk about volume, volume of a substance is obtained by combination of three similar quantities, where I said that volume is length times weight times height. These three parameters, if you combine it together, it gives you volume. And the three parameters are fundamental quantities. They are all are what? Length. Okay, so let's get to the board. Like I said, derived quantities are quantities that are obtained by combination of two or more fundamental quantities. Now we have many examples of them. We have area, we have volume, okay? Then we have speed, we have velocity, we have force, then acceleration. Let's also talk about pressure. Now these are what? Physical quantities that are derived. Hence they are called derived quantities. We have numerous of them, but we are considering only but few. Now let's see why these are regarded as derived quantities. Now let's start with the area. So for the area, we have area as the product of length and width. Now coming to the length, we have the unit of length to be meter. Then we have the unit of width to also be what? Meter, because width talks about distance between two positions, just like length also talks about distance between two positions. So width and the length, both of them are what? Distance between two positions. Now in that case, we have the unit as meter squared. This is the unit. That's the unit of area. Now, the dimension of meter, that's the dimension of length, is what? L. That's the dimension of length. Now we have meter squared. Hey, therefore, we are going to have L squared. So this gives the dimension of area. Now we have L squared, 2 of what? L. Hence, area is a what? Is a derived quantity. Now let's also look into volume. Now volume is a product of length, width, and the height or breadth. Now, the unit of length is meter. The unit of width is also meter, and the unit of height is meter. Hence, we are getting what? The product as meter cube. Now, this meter cube is a what? Is a unit known as derived unit. Is a derived unit. Now, when you take the L, the dimension of meter is what? Is L. Now, meter cube, now we have L cube. Now, this gives what? The dimension of volume. Now let's come to speed. Now we have speed. The symbol of speed is v, right? So we have speed as a distance covered in a specified time. Now, the symbol of distance is s. The symbol of time is t. Now, looking at this, distance is a fundamental quantity because it talks about length of a substance. Time is also a fundamental quantity because it talks about time, duration of an event. So distance has unit as meter. Time has unit as second. Now, meter divided by second will give what? Meter per second. Now, the unit of speed is meter per second. Now, the dimension of meter, this one now is what? It's units. So, the dimension of meter is L. The dimension of time, second is time. Then we have t raised to the power minus 1. So, this gives what? The dimension of speed. So you now see is a combination of what? Length and the time. Both of them are fundamental quantities. Hence, speed is a derived quantity. Now, let's also talk about velocity. Although velocity is similar somehow with speed, just that speed is a scalar quantity, it has no direction, while velocity is a vector quantity, or you said is a speed that has direction. Hence, we have velocity as a displacement, the displacement per time. Now, displacement is also the distance in a specified direction. So in that case, the displacement is still the same thing as distance, just that it has direction. Then the time also measured in seconds. So we have velocity having the same unit. Displacement is measured in meter. Time is measured in seconds. So we also have meter per second. So this gives what? The unit. Now the dimension of velocity will now be, dimension of meter is L. Dimension of second is time. We have minus 1. So this also gives what? The dimension. So you now see that velocity and the speed, both of them have the same dimension. Then what about acceleration? Acceleration. Now, acceleration is a rate of change of velocity with time. Hence, we said is a velocity per time. Now, because we've known the unit of velocity, meter per second, so we can get the unit of acceleration as velocity has a unit meter per second divided by time. Unit of time is second. Now, if you divide this from the rule of third, if this s should come up, it becomes x raised to the power minus 1. So, x raised to the power minus 1 times another x raised to the power minus 1, it will give us what? S raised to the power minus 2. Now, this gives what? The unit. We have the unit of acceleration. Now, having got the unit of acceleration, we can now say that the dimension of acceleration now is what? Is dimension of meter is L. Dimension of second is t. Then we have t raised to the power minus 2. We have force to be product of mass and the acceleration. Now, mass is a fundamental quantity. Acceleration is a derived quantity. Now, we know the unit of mass. What's the unit of mass? The unit of mass is kilogram times. What's the unit of acceleration? Its unit is meter per second squared. So we have meter per second squared. Now, if you multiply the unit, we are getting kilogram meter per second squared. So this gives what? The unit of what? Of force. Now, the dimension of force will now be what? Kilogram. Dimension of kilogram is capital M. Dimension of meter is L. Dimension of second is T. Hence, we have minus 2 on top. So this gives what? dimension of force. Now, the unit of the force, which is kilogram meter per second squared, has its standard units to be Newton. So, if you are now asked to find the units, SI units of force, that should be Newton. Okay? Why the derived unit of force is kilogram meter per second squared? So what it means is that 1 Newton is equal to 1 kilogram meter per second squared. Now, having mastered that of force, now let's get to pressure. We said the pressure is a derived quantity. What makes it a derived quantity? Now, we have pressure to be force per unit area. Now, what is the unit of force? The unit of force now is what? Is, look at the derived units. Kilogram meter per second squared. Now, divided by area. What's the unit of area? The unit is meter squared. So at this point, we are going to cancel one of the meter here, cancel one of the meter. So in that case, we have kilogram per second squared divided by meter. And if you do that, you are going to have kilogram. Bringing this m up, we have m raised to the power minus 1. Then second, we have minus 2. So this gives what? The units. It gives the units of pressure. So if you are now asked, although the unit of pressure being kilogram meter per second squared, we have SI unit of it, which is Pascal. So we have 1 Pascal being equal to 1 kilogram per meter per second squared. Now, what's the dimension? The dimension of pressure now becomes dimension of kilogram is what? Capital M. Dimension of meter is L. We have minus 1. Dimension of second is T. So we have this as the dimension of pressure. So to be continued, if what we did was able to help someone out there, please subscribe, share, and turn on notification for others to learn as well. See you on our next class.